Okay, so before we get too far into next year on momentum, so let's talk about the number that's written up there on the board and the whole solar project. So the short version of this very long story is that in 2018, we started the May Solar Foundation. And I went to the school board and I basically said, hey, here's the story. I've never had kids of my own, but I've taught in this district since 1993. And this is the legacy that I want to leave for not only you kids, but for your kids and your grandchildren, because I spent hours upon hours upon hours looking at the data and all the research. And it's just like, we can't keep producing electricity by burning fossil fuels. So I said, let me start this. I've taught phenomenal kids. Just let me go. Just turn me loose. I said, don't ask me for a plan. I don't have a plan. I have no timeline. I just know it's going to work. And they said, hey, go knock yourself out. What's the worst that can happen? You know? So it was one of those deals. I was too stupid to know that I could fail, because if I had thought too much about how everything could go wrong, I never would have started the project. So short version is, we started in January of 2018. By about 7 months later, we had raised over $130,000 at that point. I met with a gentleman, president of ICM. Without going into tax code, he financed the project, which allows us to save $120,000 because there was 30% federal tax credit, so it was a $400,000 system. So we got we basically got a $400,000 system for $280,000. And we're paying that back over 6 months, or excuse me, over 6 years, with the savings that we realized from that array is more than what we're paying back. And then after 6 years, we'll own the system outright. And then the district has since realized the savings that solar can generate, and so hopefully by the end of November, when you pull into the parking lot and look at the roof of Cray Woodman, that should be covered with solar panels as like the mixed system. This system saves about $32,000 a year. That system will save about $25,000 a year. So this is how this plays out with all of you. So this journey has become much more spiritual than I thought it was going to be, in terms of how it impacts my students, how it's impacted me, how it's impacted the people that heard the story. So if you've seen this, this is one of the memorial panels that's in the front of the entrance when you walk in. And so this was my mom and dad. And so let's talk about this one that says unless. So if you've ever read the Dr. Seuss book, The Lorax, and one of the lines in the story is that unless people begin to care an awful lot, nothing will change. And so this was donated by Katie Riffle. And Katie Riffle helped me hang that stapler and pulley system many, many years ago. So Katie didn't want her name on the panel. She just wanted the word unless. And so that's what that's from, because she realized she's got a degree in biology from the University of Missouri. And Katie's the same mindset that I am, that, unless things change, we have to do something different. And so that's why that word is here. So this up here is like the first group of classes that I was teaching at the time. First block, honors physics, third block, and then AP physics. And so if you look, most of my classes have panels up there. So this is strictly up to you all, okay? This is up to you all. You all need to make this decision. So if you just came and said, hey, Burkamp, I want my own panel, that takes a donation of $740. I don't expect you all to come up with $740. So what I do is I take the number of kids in the class and say, okay, on average, if people donate $20, then, which in your case is that number up there. So I took the number of kids in the class, multiplied it by 2, that's what I got that. So Morel has already donated $50 because I wrote a letter of recommendation for her. So that's why that number has already been subtracted out.
Don't forget that also $10 from your birthday.
I donated 11.
10, 11.
Okay, all right, I'll add that. I'll add that to that. Okay, so I forgot about that. So we'll add that as well. So you guys are actually already on the board. So I'll look at other classes. So what you'll see up there is, and generally there's the solar merch, there's sweatshirts, there's t-shirts, there's long sleeve t-shirts. We added this one, it's a color changing t-shirt, if you've never seen that, it's really cool. It looks like a black and white outline until you go out in the sun and then it changes color, okay? It's actually pretty cool, it was cooler than I ever thought it was gonna be. And written on the back of it is one of the quotes that came out of this. It was John Cole, who was sitting right where Maggie sits right now. And when I started the project, John was very astute, and we were talking about the carbon dioxide reductions that this would cause. And he goes, Burkamp, you know it's just a drop in the bucket. And I said, you're right, John, it is, but it's my drop, and it's my bucket, and this is the drop that I want. And if enough people make it, put drops in that bucket, then you see change. And so that's what that line is on the back of the shirt. It's sitting, John Cole's name right where Maggie was. So generally, I get about $10 per item. And so like if you buy like a shirt, sweatshirt, something like that, then that will count about $10 towards the total, okay? I just need to know what the order is by this Friday, because that way I can get that in. And you can get that back well before Christmas. Once the book becomes available, if you want to buy a book, then that's cool. That'll get me about $10 as well. Or if you just, some of you already made a donation. So you don't have to, okay? This is a collective decision that you all need to make. I don't want one person bearing the brunt of this. It's not fair to everybody else. But collectively, you all need to decide, like, hey, is this something we want? We want to be able to come back for our 10-year class reunion and go, hey, there was the physics class that I was a part of, okay? That's something that collectively you all need to decide. And if you have friends that want to buy some of the solar merch, I will, and if you can recruit them to buy stuff or buy a book or whatever, I'll count that towards your class total. So there's some options that we can go with on that. So anyway, we'll talk more about that on the Friday before Thanksgiving. But that's kind of the short version, and that's why that's up there. So I've got order forms, I think they're somewhere in there. There's a bunch of order forms. So yeah, they're there. So, and that's what it looks like over there on the wall. So, okay, so stop that. I gotta hand that selection. One of them is.
Why is it so dark?
I don't know, just,
Is it dark in here today?
Okay, everybody needs to donate $16.77.
okay, so here's the deal. So here's what we have left. We have this momentum unit, which is relatively short. It's going to take us about 7 or 8 days to get through that, so that'll put us to test with that before Thanksgiving. And then after that, then there's kind of some shorter units. We've got one on energy, we have thermodynamics, we have gas laws from the physics perspective. And then the last 5 days, we'll have a review, you have a written final, and then you have a 3-day lab final. So that's how the last 5 days of class will play out. So we've still got a ways to go, but momentum will be the kind of the last kind of big unit. Energy is as well, but energy is more diverse. Okay, so when you talk about momentum, and it's funny, if you watch like the Kansas City Chiefs game last night, or if you watch any sporting event, you know, the commentators will talk about, oh, you can feel the momentum change, right? And you can physically feel that if you've watched sports or played sports, you know, you can physically feel that happening. And so momentum from a physics perspective, in terms of the equation, is one of the easiest equations you will ever see. Momentum is simply mass times velocity. That's it, okay? Nothing complex, it's just mass times velocity. So if, let's say for example, I have a 1 kilogram mass, and it's moving at, say, 3 meters per second. So this is the easiest calculation you will have. Oh, 1 kilogram times 3 meters per second gets me 3. Now, when you write the units for momentum, there's 2 options that you can have, and I care not which one that you pick. One option is you just go, oh, that's kilograms, meters per second. Now, that is not acceleration, because acceleration would be kilograms meters per second squared. Okay, so this is just kilograms meters per second. So that's one option. Okay. Now, the other one that you can do, and later on you'll see why this works. The other option is that you do 3 Newton seconds. Okay, and the reason that works in terms of the units is newtons are kilograms meters per second squared. So if I take kilograms meters per second squared times seconds, I cancel out one of those, I get kilograms meters per second, which is the same thing as that. So I don't care which one you write down, it makes me no difference whatsoever. Either kilograms meters per second or Newton seconds, it's a personal preference thing. Now, is it possible for a smaller mass to have the same momentum as this 1 kilogram mass?
Yeah.
What would have to happen?
Velocity change.
This would have to be going
Faster.
faster, okay? So because momentum is mass times velocity, so if I want the same momentum, I could have a small mass moving quickly, or I could have a large mass moving slowly, okay? So this could have the same momentum as this. I would just have to have the velocity to make up the difference between the two. Okay, pretty simple. Do you think momentum is a vector quantity or a scalar quantity? Sam,
Scalar.
why?
It doesn't have direction.
Really? So if I take this 1 kilogram mass,
I'm gonna say it's a vector quantity.
no, we started down this road, we're gonna finish this road, okay? So if I make it go this direction, it has a positive velocity, right?
Yeah.
If I make it go in this direction, it's gonna have a,
Negative.
So could momentum be a negative value?
I'm gonna say it's a vector quantity.
I would say you're correct at this point. So if momentum is mass times velocity, because velocity is a vector quantity, I could take that 1 kilogram and I could multiply that by negative 3 meters per second, and oddly enough, I would get negative 3 Newton seconds. So momentum is very much a vector quantity. So if you think about it, when you drive, okay, sounds odd, but when you drive, you have 3 ways to fundamentally change momentum vectors, okay? What's the function of your gas pedal?
Speed up this.
Speed up, to make the momentum vectors get bigger, okay? What's the function of the brake?
Slow down.
Slow down to make your momentum vectors get smaller. What's the function of the steering wheel?
Turn.
To change the direction of your momentum vectors, okay? So fundamentally, when you're driving, you're deciding, A, I'm going to change my momentum vectors. What's the rate of change in my momentum vectors? And am I going to change the direction of the momentum vectors? So that's what you control. It's all about what are you doing with momentum vectors. Now, would it be possible for this 0.2 kilogram mass to have the same inertia as a 1 kilogram mass?
No.
No. Why?
Because mass and inertia are directly related.
Yes, the only thing that determines inertia is mass. So this 200 gram mass is always going to have less inertia than the 1,000 kilogram mass. Okay? Can't balance those out. So 2 objects of unequal mass can have the same momentum, but they can never have the same inertia. Now, on the test coming up in about 8 days, I know you would like this, where I would give you 30 problems just dealing with mass times velocity. Oh, here's the momentum and velocity, calculate the mass. Here's the mass and momentum, calculate. No. Okay. No. I know, it's like, oh, that was short-lived. But it forms the basis of something important. So here's the deal. Is it possible to change the momentum of an object?
Yeah. Wait. Yeah, you can, right?
Yeah. Okay, don't make this difficult. Okay, momentum is mass times velocity. Now, what we're always going to assume for now is that the mass is going to remain constant. Okay, so we're not going to change the mass. Rocket engines work by changing that, but we'll get into rocket engines later. So for now, we're always going to assume that the mass is going to remain constant. So let's say, for example, I take this golf ball and I throw it up in the air. Does the momentum change?
Yes.
Yes. Why?
Velocity.
Velocity change. Now, what you'll see, there's a bunch of different ways that you can calculate change in momentum. The simplest way is that it's momentum final minus momentum initial. Okay, that's the simplest way to look at it. Just like the change in anything is final minus initial. Well, you can also write that as mass times velocity minus mass times v naught. Okay, you can write it that way. It means the exact same thing. Or you can get fancy and calculate and factor out that mass and write it as v minus v naught. And if you really wanted to shortcut that, you could write that as mass times delta v. Okay, so all four of those mean the same thing. Final minus initial, change in momentum, mass times delta v, just depends upon the situation. So, the other side of this is that it also equals force times time. And technically that's going to be net force times time. So let me give you a simple example. So, Wyatt, I need you to stand up. And I've got 2 eggs. One is hard boiled and one is raw. How can I tell the difference? If I spin them, okay, so I'm going to take this one and spin it. That spins really, really quickly, okay? If I spin this one, it spins much slower, but if I stop it, it continues to spin. With this one, if I spin it and I stop it, it just stops. But this one, if you spin it and stop it, it'll continue to spin. So that's how you can tell that the one that's raw and the one that's hard-boiled. Hard-boiled one spins much faster. The one that's raw, if you stop it, it continues to spin. So I'm going to throw this to you, the raw egg. Okay? Raw one.
No.
Okay, that's
How
move over
did
here.
you
Okay, get the board out of the way.
Why would you need to check if the egg is hard boiled?
Now,
You got it, Wyatt.
don't crack the egg. No pressure. No pressure. All right, you ready?
This is the real egg.
Okay, now, fantastic. Put that back. Okay, we're good. Now,
That's it.
Wyatt perfectly demonstrated force times time. Okay? He perfectly demonstrated this. Wyatt has never seen force times time equals change in momentum. We've never talked about a force time momentum graph. We've never talked about rate functions, nothing. But he intuitively understood this equation. So here's the deal. So change in momentum also means the word impulse. So this is technically known as impulse theory. So here's what happened. So I took the egg from rest, right, and I gave it a certain velocity. So I exerted a force over a certain amount of time to create a change in the momentum. Okay? So what Wyatt did when he caught it, why did you create it like this? Why didn't you just go?
So then just crack when it hit my hand.
So what were you trying to reduce? Force or time?
Force.
Yeah, he was trying to make the force smaller. So here's what happened. Let's say here's the egg, and we'll make the math easy and say it was coming in at 0.1 kilograms. Okay, there's the mass. And it was traveling at 5 meters per second when I threw it to Wyatt. Okay, so he started off here. I started off at 0. I threw it to him. I took it from 0 to 5 meters per second. Okay, so Wyatt, when he caught it, took it from 5 meters per second to 0. So one thing we could look at is that we could look at a velocity time graph. So I took it from 0 to 5, and then it traveled through the air, and then Wyatt caught it, and he took it from 5 back to 0. Okay? That was what happened. From 0 to 5, whoop, 5, whoop, 5 back to 0, right? So, did I make the egg accelerate?
Yes.
Yes. What was the initial velocity of the egg?
0.
0. I threw it, right? I made the egg speed up. True? Okay? So then we're moving at a constant velocity, then Wyatt made the egg slow down, right? So I made it speed up, Wyatt made the egg slow down. Okay? Good with this. Now, here's the deal. You can also look at this on a momentum time graph. Think, ooh, here's a new one. Okay? So what was the initial momentum of the egg? 0, right? So if I take 5 meters per second times 0.1, I get, oddly enough, 0.5 Newton seconds. So I took the egg from 0 up to 0.5 Newton seconds. That's what I did. I took it from here, boom, through it. Travel through the air, we had a horizontal line. Wyatt caught it, and he took it from 0.5 Newton seconds to 0. Okay? So my impulse, which is change in momentum, is the exact same as Wyatt's. The signs were opposite, but the magnitude is the same. Okay? Now, let's make the math easy. Let's say it took me 1 second for me to throw the egg. Okay, so here we started the stopwatch, and it took me 1 second. So this is 1 second, 0.5, and we started at 0, 0. So do you have enough information to calculate the slope of that line?
Yeah.
Yes. What would the slope of that line be?
5 or 0.5. Yeah, there's a point in there.
So it would be change in y over, which would be 0.50 Newton seconds divided by,
1 second.
second.
so what's going to happen?
It goes into force.
Seconds cancel out. I get
Force.
0.5 newtons, which oddly enough is
Force.
the amount of force that I exerted on the egg. Okay? True? True with that. So the slope of a momentum time graph gives you net force. Now, notice that there was a horizontal line. So what's the slope of a horizontal line? 0. Guess what? There's no unbalanced force. Gravity was acting down on it, okay? It was technically maybe accelerating a little bit, but in terms of what we were doing, we just assumed that that velocity was constant, okay? Now, Wyatt catches the egg. Now, Wyatt just said that he cradled that egg to decrease what?
Force.
Force. So there's two options when Wyatt caught that egg, and I'm going to draw this a little bit bigger. So here's this momentum time graph. So I throw it, it goes to Wyatt. There's two options how Wyatt can catch that egg. Option number one, he just puts his hand out and catches it just like this. Okay, no cradling whatsoever. That line would look something like this. Okay? Wyatt cradled it. So what were you trying to do with time? Make the time bigger or make the time smaller?
Bigger.
Bigger. So when he cradled it, it looked something like this. So there's the cradle, and there's just no cradle. Right? So, listen to me very carefully. Here he catches the egg like this. Here he cradles it. In which situation, listen to me very carefully what I'm about to ask you. In which situation is there a greater change in momentum? Without the cradle, with the cradle, or is the change in momentum the same?
Same.
It's the exact same change in momentum. Okay? Because it's still going to go from 0.5 to 0. So I'm still going to have the exact same change in momentum. But when you look at force, force is, one way you can look at force, is it's a rate function. It's the rate at which the momentum changes. So in this situation here, what do you notice about the rate of change in momentum? Very rapid or very small? Rapid. So this is a big rate of change in momentum per unit of time. Big change in momentum of time equals big force. Here, this is a small rate of change in momentum per unit of time. Therefore, that is less force. So what Wyatt did without knowing it, he says, oh, Mr. Burkamp, I'm trying to make the momentum time graph more shallow because that's going to decrease the slope of the line, that's going to decrease the force, therefore the egg won't crack. Okay? So you all intuitively understand this equation. I just have to convince you that you know it. Now, here's the other way that you can view this. It's kind of cool. So we're going to look at a force time graph. Okay? So I'm going to give you two ways that you can do this. So let's look at the units. So if I were to find this area, okay, what would I multiply together? Force times time, and I would get units of Newton seconds. So Newton seconds, remember, was the same units that we had for momentum. So here's an interesting thing. So what Wyatt did, without knowing it, he says, Mr. Burkamp, I'm going to have a certain change in momentum. I want to have an area that's created by a small force acting over a long period of time. Okay? So this area here, the area equals change in momentum. So what Wyatt did, without knowing this graph, that's what I said, you all intuitively understand this. Okay, I just have to convince you that you understand it. So what Wyatt did, he goes, Mr. Burkamp, I'm going to have a small force acting over a long period of time. Because if Wyatt had just caught it with no cradle, look what would have happened. He would have had a big force acting over a short time. That would have cracked the egg. So in both situations, the area is the same. Okay? It's the exact same area. So what Wyatt did, without knowing any of these calculations in his head, he goes, I want to increase time. So he did not, listen to me, he did not decrease the change in the momentum. The change in the momentum is a fixed value because that egg's going to come into a certain velocity and it's going to stop. Okay? So what Wyatt did, he says, Mr. Burkamp, I want to create this area by having a small force acting over a long period of time. Because if I have a big force acting over a short period of time, I'm going to crack the egg. Okay? So when you cradle something, you do not do that to decrease the change in the momentum. You do that to decrease the rate of change in the momentum. You see the difference between the two? Okay, so make sure I've got the right egg. Okay, so let's see how this goes. All right. Even though you're soccer players, I trust you. Come on, you need help. So, hold up this like so. Okay, so. No. Rotate that like, yeah, that'll work.
It's quite a
Hold
nice
that.
blanket.
Then hold that bottom. So turn about 90 degrees. Yep. You come this way. Okay. So there you go. All right. So here's what I'm going to do. Now make sure I don't lower that. So just a little bit. There you go. Raise it at the bottom just a little bit. Okay. So I'm going to take the egg and I'm going to throw it into the blanket. Okay. Am I going to change the momentum of the egg?
Yes.
Yes. Is the blanket going to change the momentum of the egg?
Yes.
Yes, hopefully. Okay? So lift up the top just a little bit. Okay? All right? So take this initially, kind of give it a nice gentle toss. Now, so just make sure
I like
that
over
you
there.
lift that bottom up so it doesn't roll out the bottom. So lift it.
Yeah, can you?
There you go. There you go. Okay. Got it? Okay. So take this. Okay? All right?
Is it a hard-boiled egg?
Okay? Now, who imparted the greater impulse on the egg? Me or the blanket, or was it the same?
Same.
Same. I took the egg from 0 to
Whatever.
10 miles an hour. The blanket took from 10 miles per hour to
Zero.
Okay, so I'm going to throw a little bit harder. Now, if this goes south, it's because the blanket comes out of your hands. Okay? So don't let the blanket come out of your hands.
Sam's
Okay,
big
ready?
head is in the way.
Okay, so a little faster.
Boom.
Okay, right? So that was maybe, I don't know, maybe 30 miles per hour. Oh, because now I'm gonna bring the heat. Okay, ready?
That was not 30 miles per
Okay,
hour.
you ready? So I'm gonna throw this thing as hard as I can. Okay?
Wow.
And no matter how hard I throw this egg, it's not gonna break. We're done, gentlemen. Now, however,
Oh,
if I
crap.
take that same egg, okay? If I take that same egg and have it fall, even from here, what's gonna happen?
Gonna break.
It's gonna break.
How do we know you're not just switching out the eggs?
He had the same egg in his hand the whole time.
There's the hard boiled. Okay? Trust me, I'm not that devious, okay? I trust physics. If I didn't trust it, I really shouldn't be teaching. So here's the deal. So I could throw that egg as hard as I wanted. Whoa. That was better than that. I could throw that egg as hard as I wanted into that sheet, and it's not going to break. However, I drop that egg from any height at all, bam, shatters. What's the difference? Is it the change in momentum or the rate of change in momentum?
Rate of change.
Rate of change in momentum. Now I've seen this experiment go wrong a couple times. So one time I was having shoulder problems, and I trusted a student to throw the egg. And we were doing it right in front of that door over there. And he guaranteed me he was like this, 5-star recruit to play third base, and he had an arm like a cannon and all this stuff. And he winds up and throws it as fast as he can. And he sails it underneath the blanket. And it hits right between like the bottom of the door and the floor. Like he couldn't have aimed and hit it any better. And there was like carnage in that room. If you've been in that room, like literally there was egg splatter from the door all the way to the lab stations on the other side. I mean, if you've ever seen like CSI where they do like blood splatter investigations, this was like carnage. It was spread out all over. The other one, this was a student, I saw this done at like a science demonstration. It was the same type of deal, and the person threw it. We were at a hotel, pretty nice hotel. And he sailed it over the top of the blanket, and it hit the wall, and it just splattered. And it was just like, you saw this egg just like oozing down the side of this hotel room. It was like, whew, that's not me. All right, yeah. So if you ever do that, it's a cool demonstration. Just make sure that you have a big blanket and then you don't miss. Okay, so are we cool with this? Now, this is why I said you all intuitively understand this. Any of you ever do gymnastics? Okay. How do they teach you to land? With your knees locked in place,
Oh God, no.
or your knees bent?
Bent.
Bent. Why?
Because you don't want to break your leg.
Yeah, because if you land with your knees locked in place, what's going to happen with the amount of time? It's going to be really, really small.
And the force gets
And the force is going to be
Very
really, really big. So when you land and you bend your knees, what are you doing to the rate of change in the momentum? You're making it smaller, okay? If you get a job as an automotive safety engineer, you wake up every morning and you go force times time equals change in momentum. So what's the function of any safety device in your car, whether that's bumpers, the seat belts, airbags, whatever it is? What's the function of every safety device in that car?
Increase the rate of change.
To decrease the rate of change in momentum, which decreases the force, and you do that by increasing the time. Okay? That's it. And seriously, if you're an automotive engineer and you're in charge of safety, you wake up every morning and you go force times time equals change in momentum. Okay, that's it. That's what you do. So here's the classic example. You're driving along. God forbid you're in a head-on collision. There's no airbags and there's no safety. And you're not wearing a safety belt because you're that cool. Okay? Does your body have mass?
Yes.
Guess what? Your body therefore it's going to maintain a constant velocity until an outside force acts upon it. And if you're not wearing a safety belt, and if there's no, the airbags don't deploy, what's gonna create that force?
Your head.
Your head, your chest, something, okay?
You'll go through the windshield.
That's why you wear safety belts. This is why there's airbags. Because yes, as teenagers, the laws of physics do apply to you, okay? You may find that shocking, but it's actually true. Okay, so let's look at the situation. So here's a truck. Make the math easy, say it's moving at 10 kilograms. Gracie, pick a number between 10 and 20.
17.
Ew.
Prime
That's her
number.
age.
Okay, so we have a car mass of 10 kilograms moving at 17 meters per second, right? And the car is going to come to a stop. Final velocity is going to be 0. So here's my V naught. So did the momentum of the car change? Yes. How do you know?
The
Because
velocity.
the velocity.
Velocity changed. Do you have enough information to calculate the change in the momentum of the car?
Yes, you do. V minus V naught over.
Change in momentum
Something.
equals two things. It equals mass times V minus V naught. It also equals
Yeah, that one.
force times time. So here's the deal. As you go through this, and as you see more and more things that you can set equal to each other, you have to focus on what you're holding constant and what you're changing, okay? And what is a factor and what is not a factor, okay? So do I have enough information to calculate the change in the momentum?
Yes.
Yes. Do I know the final velocity?
Yes.
Do I know the initial velocity?
Yes.
Do I know the mass?
Yes.
Now, here's what you're going to do wrong. And you all sit there and go, Mr. Burkamp, we won't do that. And you lie. Okay? You're going to go, oh, 17 times 10. Change in momentum is 170. Bad. Bad.
So embarrassing.
You all sit there and go, we won't do that. Yes, you will. Okay?
I would never do that ever.
Now,
Final
is
numbers.
170 the initial momentum?
Yes.
Yes. It does have a momentum of 170. But is that the final momentum?
No.
What's the final momentum?
0.
0. So you're going to take, you can do this a couple of ways. You can take 10 kilograms times 0 minus 17, and you can get negative 170 Newton seconds. Okay? You could take 0 minus 170 Newton seconds, and you can get negative 170 Newton seconds. If you're a graphing kind of person, like, well, Mr. Burkamp, I like graphs. Good for you. Okay? So you're going to start up here at 170 Newton seconds, because this is a momentum time graph, and it's going to come down here like this. And that change in momentum would be 0 minus 170. I don't care how you view it. Pick one. Doesn't make any difference. But do we have enough information to calculate the force acting on the truck? No, because what do we not have? Time. Okay. Cooper, pick a number between 1 and 8.
4.
Okay. So let's say that it took 4 seconds for the truck to stop. Now if I know the time, could I calculate the force? Yes, because what we're saying now is that here's the force time graph, okay? And we're going to exert some amount of force over a time of 4 seconds. Now, what does that change in momentum represent? The area. So the area here is going to be negative 170 Newton seconds. So right away, what do you know about the sign of the force acting on the truck?
Negative.
Has to be a negative value. And hopefully this makes sense. Oh, this thing is moving with some positive velocity. And we're going to stop it, right? So which direction does the force have to act? Opposite direction. So if you screw up and you go, oh, that change in momentum is a positive value, here's what you're telling me. You're going to stop a truck moving with a positive velocity by pushing it in the same direction that it's going. Cool. Not going to work. Okay? So this is why it's so important that you pay attention to the sign. So, if you're into area, the area is negative 170 Newton seconds. That equals 1 dimension times 4 seconds. So somebody take negative 170 and divide that by 4. What'd you get? Negative 42.5 newtons. Okay? Cool with that. Right? That makes sense. Oh, right. Positive velocities, moving. We're going to stop the truck. We have to apply a negative force. That has to be going in the opposite direction. Cool. Now, listen to me very carefully. What if, instead of choosing 4 seconds, Cooper says, I'm going to make that 8 seconds. Okay? Cooper makes that 8 seconds. Now listen very carefully. What's that going to do to the change in the momentum of the truck? Increase it? Decrease it? Or it's still going to stay the same?
Stay the same.
Stay the same. Why?
Because time is not part of momentum.
Because if you look at how we calculated momentum, because we chose mass times delta V, notice that time is not a factor. So the 8 seconds doesn't matter. The change in the momentum is still negative 170. That hasn't changed. Still the exact change in momentum. It's just like if Wyatt catches the egg. Whether he catches the egg like this or if he cradles it, it's still the same change in momentum. But by increasing the time, what are we doing to the force? It's going to become smaller. So now, somebody take that same negative 170 and divide that by 8 seconds. Negative 21.3 newtons. Now, here's the cool thing about this. If you were to look at this in terms of a momentum time graph, okay, I screwed that all up. A momentum time graph. So in both situations, you're starting up here at 170. So in situation number 1, that's going to take you 4 seconds, right? And the slope of that line is going to be negative 42.5 newtons, okay? Because that's the force, because the slope of a momentum time graph gives you force. So the other option is that it takes you 8 seconds. So look what happens to the slope of that line. That line becomes less because of the fact that it's still the same change in momentum, it's just less force. Now, that's a decision that you all make every time that you drive. You're driving along at 40 miles an hour, okay? A little squirrel runs out in the road. You like squirrels, okay? You're a humanitarian, you're a good person. You hit the brakes. You go from 40 to 0, right? Pretty rapidly. You slam on the brakes, right? That's a big force because you want to have a rapid change in your momentum vector. Other option, you're driving at 40 miles per hour, you forgot to put gas into the car, and it runs out of gas, okay? And you want to coast as long as you can, okay? So you're not hitting the brakes at all. You're just going to let friction stop you, and you're going to coast as long as you can. In both situations, you're driving 40 miles per hour. Option A, squirrel, bam, hit the brakes, okay? Option 2, ran out of gas, we're going to coast, okay? In which situation is there a greater change in momentum? Squirrel, no gas.
Neither.
Neither. Same change in momentum. But which one is going to require more force? Squirrel, no gas. Squirrel. Okay? Because you go from 40 to 0 rapidly because you like squirrels and you're good people. Okay. Now listen to me very carefully on this next question. You want to create a big change in momentum. You want to create a big change in momentum. You can have a small force acting over a short period of time. You can have a large force, small period of time. You can have a small force acting over a long period of time. You can have a small force acting over a short period of time, or a large force acting over a large period of time. So big force, small time, Small force, big time, small force, small time, big force, big time. Which one will create the biggest change in the momentum?
Is it big? Wait, big force,
Big force,
time?
big time, why?
Because it would be like they're multiplying by each other, so it's increased, right?
Yeah, so remember, on a momentum time graph, what does the area of a momentum time graph give you? Excuse me, force time, I'm sorry, force time. Change in momentum, right? So if you want a big change in momentum, you want the biggest possible area. And you decide this when you drive, okay? You get in your car, you get out, light turns green. So if you press down on that gas pedal, you're creating a big force. And if you hold that for a long period of time, you're going to create a big momentum. Now, if you just go barely tap the gas pedal for just a short amount of time, guess what? You're not going to create a very big change in momentum. Okay? So that's why as we go through this, it is vital that you focus on what you're holding constant and what you're changing. Okay? All right, so stop yonder camera. I'll give you some hints on some of these. On the question about the mass of the inertia with the elephant and the mouse, don't get picky and go, well, if the elephant's just a tiny embryo and you've got a big Texas-sized mouse. No, okay? It's a mouse and an elephant, okay? Right? Don't get technical on that. When you get to question number 3, visualize, this is for those of you that might not necessarily be familiar with baseball. So here's the picture, right? So you're starting here like this, and you have to go through this whole wind-up process and go through this whole process of throwing, right? The catcher is here, the catcher just goes, bing, okay? So pitcher, big wind-up, takes a long time. Catcher stops it just like this. So keep that in mind on that visual. When you get to question number 12, okay? Soccer ball is rolling, it's moving at 6 meters per second. It kicks the ball, it goes in the opposite direction. So why did I have to change that velocity from 6 to negative 14?
Because it's a vector quantity.
Because it's a vector quantity, okay, and it changed direction. So that's why that velocity switched from 6 to negative 14. Okay, I'm done. You're on your own.